Welcome. This question says a 4 kilogram hollow hoop that has a 2 meter radius is placed at the top of a 30-meter tall ramp. It rolls to the bottom of the ramp without slipping. What is its speed at the bottom of the ramp? So if we visualize this, we have 30 meters, and then we have the hollow hoop here. We let it go. It's down here. It has a velocity, and we want to find this velocity down here. It's to do with conservation of energy, isn't it? It's an isolated system, so I can say my mechanical energy at the initial is equal to my mechanical energy at the final. And if I look here, it starts off from rest. There's no information about having an initial velocity, so it starts off from rest, but it does have a higher position in a gravitational field. So this would be mgh, if you like, h initial, is equal to, forget about kinetic energy because it starts off stationary, and then this is going to equal to the end position, and at the end position, it's at the bottom of the ramp, so we can forget about the gravitational potential energy. It has got two contributions to its kinetic energy though. There is K translational plus K rotational. It's not sliding down, it is rolling down. So mgh is equal to 1/2 mv tran squared plus 1/2 I omega squared. We've seen this before. So mgh is equal to 1/2 mv tran squared plus 1/2. Now, this is a hollow hoop, so its moment of inertia equals not 1/2 m r squared, but simply m r squared. Remember those, the moment of inertia for a solid cylinder, a hollow hoop, and a solid sphere. We should commit to memory. And then we have to work into account, we'd like to express this angular velocity in linear terms. So this would be v tangential over r, and of course this is squared. So those are those two conversions we need to do. Let's write this down. mgh is equal to 1/2 mv tran squared plus 1/2 m r squared v tang squared over r squared. Remember, when you're squaring something in a bracket, you've got to square both the top and the bottom. If I look on this, I can see that that radius disappears. And so and also I can actually see that this mass cancels out these masses. Every term has mass in it, so it doesn't matter about the mass. And the third thing is that the v translational is the same numerical value as the v tangential. And if you're not sure about that, get yourself a roll of tissue and unroll it and just convince yourself of that. So then we simplify and we go, well, GH is equal to 1/2 v, we can just call it v because the translational is the same numerical value as the tangential. A half v squared plus 1/2 v squared, which equals v squared. So v squared is going to equal 10 times 30, which equals 300. So v is equal to the square root of 300, which equals, if my calculator helps me out here, 17.32. 17.32 meters per second. Yeah, the square root plus or minus 17.32, but we're looking at a speed which is a magnitude, so that would be plus 17.32 meters per second. And as usual, we always run our numbers on a little bit. We can't justify it based on, we got one significant figure and one significant figure and one significant figure. So in terms of significant figures, we should only have one significant figure in our answer. But, you know, in order to help, I don't want to give you difficult original numbers to get a more involved final answer. So we just let it run on for a few decimal places. But there we have it. This is a typical rolling motion problem. We recognize that the mechanical energy at the initial position equal to mechanical energy at final position. We were able to express this in terms of terms for our gravitational potential energy, our translational kinetic energy, and our rotational kinetic energy. We were able to bring in conversion factors for the moment of inertia for a hollow hoop and the angular velocity in terms of the tangential velocity and the radius. We were able to see that numerous things cancelled, in particular the mass cancelled, which was not obvious. And the rest was just basically doing our sums. Notice from an exam point of view, I need not give you the mass because it's not involved in the final answer. And if you're not thinking in complete sentences, if you're trying to work out the gravitational potential energy and then in your head saying, well, that's equal to these other bits, you get to the bit where you're trying to work out your gravitational potential energy and you can't do it because there's no m. And then you say, well, okay, let's try and do at least the translational kinetic energy, and you can't do that because there's no m. And it's very often a student will say to me, well, you know, I can't do this problem because you didn't give us m, and I'll have to just smile and say, well, do your best. But if you think in complete sentences, if you think in terms of a principle, and then you write down a complete sentence rather than little phrases, you can see, oh yeah, the mass cancels. And that's where we're trying to get you to go. We're trying to get you to think in complete sentences. So there we go.